Okay, in this lesson, we are talking about rational exponents. The goal is to be able to simplify and evaluate expressions with rational exponents. So it's important that you understand where a rational exponent comes from. So we have this definition here. Get my pen going. So let a to the 1 over n power be the nth root of a. So a is basically your base. N is the root. So the root is the number that's in the denominator of the fraction of the exponent. And let m be a positive integer. So that's for this example here. So a to the m over n power, there's a couple ways you can write it. You can write it as a to the 1 over n to the mth power, and then the nth root of a to the mth power. So there's various ways of expressing these things, but one thing that's important for you to understand is that this n is the root. So the n here is the root, and the m is the power. So there's, like I said, different ways of expressing it, but in all three cases, a is the base. So the root in radical form is right here. It is also called an index, and you can see the power is out there. So one of the things that hopefully you've learned from the past is that a square root, we'll use a for our variable, is actually has a root of 2. So the unwritten root, if there's no root written in the index, it's understood that the root is 2. And this is in radical form. When we write it in rational form, or as a rational exponent, we write a to the 1/2 power. So the root of 2, which is in the index, is the denominator of your exponent. So if the square root of a equals a to the 1/2 power, then the cubed root of a equals a to the 1/3 power. And so on. The nth root of a then is equal to 1 over, I'm sorry, that's not what I meant, a to the 1 over nth power. So whatever the root is in radical form becomes the denominator of the exponent, of the rational exponent. So when we start having things with a power and a root, so for example, a to the m over n power, like I said before, the n is the root and the m is the power. And when you rewrite this in rational or as a radical, the n is the root, goes there, and the base goes here. The power now could actually go here. Let me make this a little bit smaller. So you could write the power right here, but you could also put this in parentheses and put the power on the outside. So all three of these expressions are equivalent. So again, just to reiterate, a little bit more space, a to the m over n equals the nth root of a to the m power, which is equal to the nth root of a to the m power. So all three of these are the same. These are equivalent expressions. I cannot spell today. Equivalent expressions. All right. We have another example over here where you do have a negative exponent. So when you have a negative exponent, that does not mean a negative number. It means the reciprocal of, or 1 over, a to the m over n power. So notice that when we move this into the denominator, that negative exponent goes away. And then again, we could simplify it as the nth root of a to the m power. Now there is a condition though here that a cannot equal 0, because if a were 0, then you would have 0 in the denominator, making the fraction undefined. All right, so these are some of the properties and the rules. So let's get to simplifying some of these. And these are things that you want to do without a calculator. You will have, because you do not want decimal answers. And also on a lot of standardized tests, they require you to be able to do things like this without a calculator. And if you have variables, of course, then this you can't put them in the calculator either. So to rewrite this expression in radical form, we would rewrite this with the 3, which is the root, would go in the index of the radical. The 64 would go in underneath, and then I like to put the power on the outside because I like to make this number smaller first by taking the root of it and then taking it to the third power. So if you think about the 64, the cubed root of 64, and to simplify it, you have to ask yourself, is, first of all, 64 a perfect cube? Well, yes, it is. 64 is 4 times 4 times 4. So if you're taking the cubed, so basically, essentially, 64 is 4 to the third power. So if you're taking the cubed root of 4 to the third power, then that would just equal 4, because the third root and the third power undo each other. But then don't forget we have this fourth power on the outside. So now, so we technically had that fourth power out there all the whole time. When you take 4 to the fourth power, you get now your simplified value of 256. Okay, so that's just one example. Let's say we have another example here with a negative exponent. So I'm going to deal with the negative exponent kind of towards the end. I'm going to take care of the root first. So I want to take the fourth root of 16 and then take that to the negative fifth power. So the fourth root of 16 means, again, we need to find a number that we can multiply by itself 4 times. That would equal 16 if 16 is a perfect fourth power. Well, it just so happens that 16, the prime factorization of 16 is 2 times 2 times 2 times 2, which is 2 to the fourth power. So when you're taking the fourth root of 16, or the fourth root of 2 to the fourth power, again, the fourth root and fourth power undo each other. So the fourth root of 16 is 2. The more you use these roots, the easier it will be to remember. Now we want to focus on the negative 5 exponent. So technically we had this exponent here carried along the whole time. Because it's a negative exponent, we want to make the exponent positive by rewriting the expression with the 1 over the 2. But now, because we're putting it in the denominator, the negative exponent becomes positive. So we're basically taking the reciprocal of 2, which is 1/2. So that's another way of looking at it. The reciprocal of 2 is 1/2 to the fifth power. So whether you rewrite it as 1 over 2 to the fifth power, or 1/2, which is the reciprocal of 2 to the fifth power, you're going to end up getting the same thing. So the 1 would stay at the numerator. 2 to the fifth power is 32. If you rewrite this as the reciprocal as 1/2 to the fifth power, and then you distribute the exponent to both the numerator and denominator, 1 to the fifth power over 2 to the fifth power, you would still get 1 over 32 as your simplified answer. Okay, so these next three problems are calculator problems. So this go around, this trimester, we are not going to be doing these. So I'm going to skip these for now because I can't show you my scientific calculator. Usually I show you how to put this in the calculator. But again, it depends on what kind of calculator you have. So this is really something we have to do in the classroom. So we're going to skip that for now, and we're going to go to this next part where we're going to use the properties of exponents to simplify each expression. So again, your properties of exponents that we looked at before, just put some of them up here, is that if you have a to the m times a to the n, it equals a to the m plus n. So even though you are multiplying, when you are multiplying things with the same base, you add the exponents. So that's exactly what we have going on here in example A. You have a base of 2, so the bases are the same. You are multiplying, which means the exponents must be added. Okay, so these are not nice whole numbers. I know we have fractions, but that's what rational exponents are. Rational exponents means fractional exponents. So now we have to add the 3/4 and the 1/2 together. But in order to add fractions, you have to have a common denominator. So the common denominator between 4 and 2 is 4. So if I multiply the 1/2 in the numerator and denominator by 2, I will get 2/4. So now I can add the numerators and I get 2 to the 5/4 power. So we are leaving the answers in simplified form, no decimals, which means you are not putting this in the calculator and getting a decimal answer. So we have to ask ourselves now, the root is 4. So is 2 a perfect fourth power? Can you take the fourth root of 2? Well, no, 2 is a prime number, so there's no way we're going to get a number to the fourth power that would equal 2. So this is simplified. Okay, the next example, we're going to use our quotient rule, which basically says a to the m power over a to the nth power equals a to the m minus n. So when we're dividing, we subtract the exponents as long as our bases are the same. So in this example, the exponent is technically 1. So when you just have a number with no exponent, it does have an unwritten exponent of 1. So the base is 3. So I would be able to take 3 to the power of 1 minus 1/4. So I'm going to subtract these exponents. So again, our common denominator would be 4. 1 is equivalent to 4/4 minus 1/4 will give me 3 to the power of 3/4. Now make sure when you're writing these that this 3/4 looks like an exponent. So you have to have, it has to be up higher. It cannot be on the same. So what I don't want to see, and this is what I see sometimes, students writing 3 and 3/4. So this number here is a mixed number. This is not the same as this. These are not equivalent. So do not write your fraction, your fractional exponent or your rational exponent down here. Make sure it's up higher and smaller, and it's easy to see that it's an exponent. Okay, so the next rule here that we're using is actually one that we're going to use. It's kind of backwards. So we have this rule that if you are dividing things with 2 different bases and you're taking it to a power, you can distribute that exponent to the numerator and to the denominator. Well, in this rule, we're actually going to use this rule backwards. So the same thing is true if you have the same exponent, you can divide the bases. Now, sometimes this is helpful and sometimes it's not, but in this problem, we do not have the same base, but we do have the same exponent, which means I can divide the bases and then take them to the 1/2 power. Now don't forget that you do have that exponent of -3 on the outside. We'll deal with that in a minute. But the 20/5 now can be divided and we get 4. 4 to the 1/2 power is the same as a square root of 4. So the 2 is the root. I could write this as a square root of 4. Either way, it's equal to 2. But don't forget we do have that exponent of -3 that we're carrying along. All right, so now we'll deal with that exponent of -3. Since it is a negative exponent, we want to take the reciprocal of 2, which is 1/2, to the 3rd power. So that negative exponent becomes positive when we take the reciprocal of the base. And then when we, again, use this rule, now we're going to distribute the exponent in. 3 to the 1st power is just 3. 1 to the 3rd power is 1. 2 to the 3rd power is 8. And now we have our simplified expression. Okay, so the next couple here, we're using a few different rules here. So you have to sometimes be creative, actually. All right, so starting from the inside out, if you look at the inside, you have -4 to the 1/3 power, and you've got 1/32 to the 1/3 power. So what do they have in common? The exponent. So when your exponent is the same, just like over here in example C, when the exponent was the same, we could divide the bases. The same thing is true when you're multiplying. If you have the same exponent, you can multiply the bases. So I'm going to rewrite this as -4 times 1/32 to the 1/3 power. And then we still have that -5 on the outside. So when I multiply -4 times 1/32, I would get -4/32, which would reduce to -1/8. And we still have the -5 on the outside. All right. So now we want to, now I'm going to rewrite this as a radical. So the cubed root of -1/8. Now you can take a negative number to an odd root. If this was an even root, then there would be it would be imaginary. If it was a square root, anyway. But when it's an even root, it would not be a real number. So you cannot take a negative number to an even root. But 3 is an odd root. So the negative number to an odd root will be negative. And then if you take the cubed root of 1, you just get 1. But the cubed root of 8 is 2. Again, because 2 times 2 times 2 is equal to 8, which is 2 to the 3rd power. So when you take the cubed root of 2 to the 3rd power, the 3rd root and 3rd power eliminate or cancel each other out, and you get 2. So you can get negative numbers when you are simplifying these things. All right, so that one was a little bit more challenging. The next one is also kind of a fun one. Let's use blue again. So this time, if you're looking, we do not have the same exponent, but we do have the same base. So when you have the same base, you want to add the exponents. All right, so when I add the exponents, the 5/4 plus 1/4 is equal to 6/4. Well, 6/4 is a fraction that can be reduced. So if I reduce the fraction 6/4, they have a common factor of 2, so I can reduce them both by 2. So now I'll have 12 to the 3/2 power over 6 to the 3/2 power. Okay, so now if you look at the problem, you have the same exponent. So now that you have the same exponent, you can divide the bases. So the 12 over 6 is 2, and then 3 halves is your exponent. Since 2 is not, so your root is 2, which is a square root, and you have to ask yourself, can I simplify this any further? Well, can you take the cubed root of, or the square root, sorry, of 2? No, 2 is not a perfect square, it's a prime number. So this is simplified now. All right, so there were a couple other problems that I wanted to add to our notes today. And let me find them here. Okay, so a couple more examples that will be helpful for some of your assignments that you are required to do on Khan Academy are, I'm just going to call this example A. And these involve variables. So the examples that I had already created from my previous notes did not have any variables. So I'm going to do a couple of examples with variables. But the same idea is true, that when you have the same base, you need to subtract the exponents when you're dividing. Again, you need to get a common denominator, so your common denominator will be 4. So 2 is technically 2 over 1, so I multiply the top and the bottom by 4, and I would get 5/4 minus 8/4. You always want to leave your fractions improper. So now when I take 5 minus 8, 5/4 minus 8/4, I get n to the negative 3/4. So you're not supposed to leave a rational exponent negative or any exponents negative. So in simplified form, you have to make this positive. So you need to take the reciprocal of the base, which is basically 1 over n. But 1 to any power is just 1. So really, we just need to take that 3/4 now and put it in the denominator. So when we rewrite this expression, since it's a negative exponent, we move it to the denominator and it becomes a positive exponent. And then that's it, because we don't know what n is. So that's all we can simplify it as. And we might want to state that n cannot equal 0, because you cannot have 0 in your denominator. All right, here's one more example with a variable. We'll call this example B. So let's say that you have 5z to the negative 3/4 power times 4 square root of z. So some of the problems that you are facing, that you're doing, have rational exponents and radicals in the same problem. When that happens, you want to change the radical to a rational exponent. So the 5z to the negative 3/4 power, we're going to leave the same. And the z has an exponent of 1/2. Square root of z is the same as z to the 1/2 power. So now the numbers in front, your coefficients of 5 and 4, can be multiplied. So 5 times 4 will be 20. But then when you take z to the negative 3/4 times z to the 1/2, you're going to have to add these exponents. So you're going to have z to the negative 3/4 plus 1/2. All right, so now we have to again get a common denominator. Our common denominator is 4. So the negative 3/4 already has a denominator of 4. Multiply the 1/2 by 2 on the top and the bottom. So they get 2/4. When you add those together, you get z now to the negative 1/4 power with a coefficient of 20. So the z, again, has to be simplified a little further because it has a negative exponent. So we're going to move it to the denominator. So when you have a negative exponent, move it to the denominator, it becomes positive. But the 20 did not have a negative exponent. That negative exponent only belongs to the z. So the only thing that gets moved down is the z. The 20 stays in the numerator. So now it is in simplified form.